Hello everybody and welcome to yet another live stream. I thought today about doing a shorter live stream about Ada Lovelace. Her story is very fascinating to me and I found it very interesting, and this is why I would like to share and geek out a bit about her and her work with computers before computers actually existed in the way we know them. Now, this was prompted by by the fact that there's Ada Lovelace Day. It was on 11 October 2022, so this is 2 days ago. I've been very busy. I didn't actually notice that it was happening. And this is an international celebration of the achievement of women in science, technology, engineering, and math in STEM domains. I think it's a really good idea. But beyond that, why is Ada Lovelace so interesting? This is what I'd like to talk about. And let's go a bit on the Wikipedia article. So Augusta Ada King, Countess of Lovelace, née Byron, in 1815, died in 1852. She was an English mathematician and writer, chiefly known for her work on Charles Babbage's proposed mechanical general-purpose computer, the analytical engine. And we'll talk a bit about the analytical engine. She's well known for writing what many people say is the first program. We will look at that program. It doesn't look like something you would write today, but it was actually an algorithm intended to be carried out by such a machine. So imagine that you know nothing about computers, you know nothing about the principles of computers. You learn about a guy, in this case Charles Babbage, figuring out and working out how to create a machine that computes things. But then what is really interesting about Ada Lovelace is that she thought beyond what the machine was meant to do. And this is actually what was very interesting. And so let's talk a bit about Charles Babbage and the machine, because that's where it all started. And for this I will go on the Encyclopedia Britannica website. And here, so Charles Babbage, born 1791, died 1871, so, you know, back then they didn't have semiconductors and things like this, and CPUs. In 1812 he helped found the Analytical Society, whose object was to introduce developments from the European continent into English mathematics. And he came to this idea of mechanically calculating mathematical tables. And then he made a small calculator that performed certain mathematical computations to 8 decimals. And then in 1823 he obtained government support for the design of a projected machine, the difference engine, with a 20 decimal capacity. So as we will see, he wasn't thinking in bits yet, in binary. He was thinking in base 10, and that's why 20 decimals. The difference engine was a digital device. Digital? How? Well, not electronic. It operated on discrete digits rather than smooth quantities. This is what digital device means. Today, all digital devices are electronic. Maybe somebody will contradict me. If you know of a digital device that's not electronic, please let me know. That would be interesting. But digital devices are electronic, but discrete means that you are in digital means that you are operating on digits, rather than on smooth quantities. And the digits were decimal 0 to 9, represented by positions on tooth wheels rather than binary digits. When one of the tooth wheels turned from 9 to 0, it caused the next wheel to advance one position carrying the digits. So basically, you know, a calculator. It would compute things. And it looked like this. Let's take a look. Part of it is in the Science Museum in London. I've seen it live. It's fascinating to me. It looks really cool. And so this is, looks like what was completed at least. So you can see numbers 1, 2, 3, 9, 0, and then these things rotate and would make the next things switch a bit when they switch from 9 to 0. And I mean, it looks pretty like what you'd expect from a mechanical machine. Now here's where it starts to get interesting. Like modern computers, the different engine had storage, that is a place where data could be held temporarily for later processing. Its construction required the development of mechanical engineer techniques to which Babbage of necessity devoted himself. So imagine having memory, like RAM or hard drive, but not electronic memory, but storing it somehow mechanically. That's what he was doing. In the meantime, okay, however, the full engine designed to be room size was never built, at least not by Babbage. All design and construction ceased in 1833 when the machinist responsible for actually building the machine, Joseph Clement, refused to continue unless he was prepaid. He was getting some grants from the government and they kind of stopped giving the grants and they weren't very reliable. Now the interesting thing, so he developed plans for the analytical engine, the forerunner of the modern digital computer. In that device, he envisioned the capability of performing any arithmetical operation on the basis of instruction from punched cards. Remember punch cards? I'm not sure you've seen punch cards, but they were used for storing programs. So the history of punch cards actually goes back before computers. I think one of the first times they were used, if I remember correctly, is for I think loom machines, I think they are called, for carpets, making nice carpets. A memory unit in which to store numbers, sequential control, and most of the other basic elements of the present-day computer. As with the difference engine, the project was far more complex than anything therefore built. The memory unit was to be large enough to hold 1050 digit numbers. Somebody compute how many bits that is. This was larger than the storage capacity of any computer built before 1960. So he actually, he was very brave and wanted to do a lot of things. The machine was to be steam driven and run by one attendant. And this is where Ada Lovelace comes in. So you have this machine who is not built. It's an idea, right? It's an idea about a machine that could compute things and could store data. So you have the fundamentals of a Turing machine. You have a storage and you have some processing. Now the processing doesn't look like in a Turing machine. Well, it doesn't look like what we know today, but it is quite close to that, right? In 1843, Babbage's friend mathematician Ada Lovelace translated a French paper about the analytical engine and, in her own annotations, published how it could perform a sequence of calculation, the first computer program. And this is so where Ada Lovelace comes in. Never seeing this machine, never working with this machine. It's a concept of a machine. It's not something that really exists. And she comes and writes the first programming language and sees beyond the limits of this machine, which at that point, let's not forget, at that point in history, the best use for such a machine was to compute things. It was meant, I think, to compute logarithms. So basically computing things. Okay, so let's go back a bit to Ada Lovelace. So Ada Lovelace was the daughter of the only legitimate child of poet Lord Byron and Lady Byron. And Lord Byron, a famous English poet, was, let's say, he had some weird ideas, and so her mother remained bitter after he left and promoted Ada's interest in mathematics and logic in an effort to prevent her from developing her father's perceived insanity. It is a really weird motivation, and I can only imagine how strange it might have been, but it's interesting because back then, of course, well, first of all, not many people were interested in sciences, and unfortunately, even fewer women were encouraged to work in sciences. So this is a very interesting coincidence, based on a bad fact, on a bad history, but something that has helped Ada Lovelace become interested in and had the skills to do mathematics and logic and programming. Her educational and social exploits brought her into contact with scientists such as Andrew Cross, Charles Babbage, Sir David Brewster, Charles Wheatstone, Michael Faraday, and the author Charles Dickens. Ada described her approach as poetical science and herself as an analyst and metaphysician. Kind of like a programmer, right? This is what we would think. All right. So 1842-1843 translated an article about the analytical engine, and she added notes. And those were the notes about the program. And now let's look a bit about the program and how the program was built, because, well, of course, it doesn't look like a program that we would be used to. But if you look at this, so this is a computer algorithm that's meant to run on that mechanical device, right? And you have here number of operations, nature of operation, and you have multiplication, minus, plus, I guess, some curly braces. Even the first program had curly braces in it. Variables acted upon, and these are some sets of variables. Variables receiving results, and these are the variables receiving results. Now, based on this, I imagine that she's talking about the cylinders and the position in the cylinders. Indication of change in the value on any variable. These look like validations or checks. Statement of results, so basically what you would compute in the end. And then you have data, working variables, result variables. So it's not a program in the sense that you would think of today. It's not a program that you would write today, like having ifs and for loops or while loops, or sequence, cycles, and conditionals. It's not like that. But it shows how you can run step by step something on a computer, which is not a digital electronic computer like we are used today, but on a computer, and get a result. This is incredible to me. So imagine that you don't know anything about computers. You read a paper and you translate a paper about how potential calculating machine might work. And then you say, oh, I can actually use that for something more than just what it is. And the goal for this was to compute Bernoulli numbers. This is the first published algorithm ever specifically tailored for implementation on a computer. And because of that, Ada Lovelace was cited as the first computer programmer for this reason. And to top this up, it's interesting to see what she thought about the analytical machine, the analytical engine. She says, the analytical engine might act upon other things besides number, where objects found those mutual fundamental relations could be expressed by those of the abstract science of operations, and which should also be susceptible to adaptations to the action of the operating notation and mechanism of the engine. Supposing, for instance, that the fundamental relation of pitch sounds in the science of harmony and of musical composition were susceptible to such expression and adaptations, the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. So she's imagining an application where she can program basically the analytical engine to create music. And this is, somebody who's never seen an actual computer, who's never seen the actual machine, but her thoughts went far, far beyond the limitations of the machine. And a comment by historian of computing and Babbage specialist Doran Swade. Ada saw something that Babbage in some sense failed to see. In Babbage's world, his engines were bound by a number. What Lovelace saw was that number could represent entities other than quantity. So once you had a machine for manipulating numbers, if those numbers represented other things, letters, musical notes, then the machine could manipulate symbols of which number was one instance, according to rules. It is this fundamental transition from a machine which is a number cruncher to a machine for manipulating symbols according to rules that is the fundamental transition from calculation to computation, to general purpose computation. And looking back from the present high ground of modern computing, if you are looking and sifting history for that transition, then that transition was made explicitly by Ada in that 1843 paper. So this is why I find Ada Lovelace so interesting. She went beyond the limitations of the machine. A machine that she didn't see, didn't actually use because it was never built. But she imagined enough to go beyond the limitations and understood that computer, in the sense that it was back then, can not only calculate but can also work with more abstract entities. And this is what fundamentally we are doing every day as programmers. We are not calculating anymore, but we are dealing with more abstract entities. And this is why I believe I find her so interesting and her story so inspiring. It's such a great story to see how you can go beyond, you know, where you are. And it's a timeless story, but in this case it happens to coincide with the field that I love, with programming. And to understand the history of programming like that, it's just amazing. So if you can, visit the Science Museum in London, where you can see the Charles Babbage machine, what was built of it, and learn more about Ada Lovelace. And let's not forget that, you see, today there's this weird debate that I hope we can put behind us of women in STEM. Of course we should have women in STEM. I mean, it's obvious. And especially when you see somebody as inspiring as Ada Lovelace, how can you not have women in STEM? I mean, it's obvious that we should. So, and with this being said, I invite you to also, since this is a celebration of women in computing, we have a number of interviews on this channel with incredible women from this field. Rebecca Worth-Brock, Linda Rising. So check them out. It's a nice thing to learn more about their contributions and, you know, about their work in this area. This is it for now. Thank you so much for watching. Thank you so much for the view, and until next time, remember to think, design, and work smart.